Hi students, welcome back. I hope you are doing good. So in this part we'll be discussing about the properties of your transition elements. So let's start with this part. Properties of transition elements. So melting point and boiling point. So transition elements have high melting point and boiling point. What is the reason? The reason is because of the strong metallic bond. So you know one important thing that when you have metallic bonds, they have strong melting and boiling points. And also another reason is that they have half-filled d orbitals. So because of these two reasons, the transition elements have higher melting and boiling point. So next important reason is that involvement of great number of electrons from n-1d in the addition to ns electrons in the interatomic metallic bonding. So what is happening is that you know that transition elements have 4s 0 or 4s 1 to 2 and 3d 1 to 10 configuration. So now what is happening is that you are actually involving this n-1 orbitals or n-1d orbitals or electrons present in the n-1d orbitals. So what happens is that as soon as you involve this greater number of electrons from this n-1d in addition to ns electrons, because of that you have the metallic bond possible. If the metallic bonding is possible, again as I already told, you have high melting point and boiling point. So because of strong interatomic bonding, transition elements have higher melting and boiling point. So the same logic. Next, so as you are moving along the period from left to right, the melting point of these elements or metals first increases to maximum and decreases regularly towards the end of the period. Why? Because as you go from left to right, initially yes you have 3d unpaired electrons, right? So for example, you have 3d subshell. So you have one electron like this, one electron like this, one electron like this, one electron like this as you go from left to right. But as soon as you go to the higher elements or from the configuration 3d5 to 3d6, filling takes place. So if filling takes place, what is happening is that as soon as the filling takes place, your number of electrons present in d orbital decreases. So if it decreases, your melting point and boiling point decreases because of decrease in the metallic bond. So you can see here. So if you can see hafnium, so you can see it goes to maximum and again decreases. The same thing happens in 3d series and 4d series. So you can see titanium, it goes and comes down for manganese, then again. So it is not a regular trend. So the trend in the melting point, boiling point, the same trend is observed even in the boiling point, right? So this is the trend of the melting point of the transition elements. So melting points of these metals rise to maximum at d5 except for anomalous. So why this is not happening for Mn and Tc? Because of their, there is an anomalous behavior even though they have a d5 configuration. Why? Because the properties of manganese and Tc. So they fall regularly as the atomic number decreases. So the trends of melting point of 3d, 4d and 5d transition elements. So from the trends we can conclude that the strength of the interatomic bonds in transition elements is roughly related to the number of half-filled d orbitals. So it is not a true logic to say that whether your half-filled d orbitals are responsible for the melting point. So this is very important. So the strength of the interatomic bonds in transition elements is roughly related. Is not truly related but roughly related. So in the beginning of the number of half-filled d orbitals increases till the middle of the period increase in strength of interparticle bonds, but thereafter the pairing of electrons in the d orbitals occurs and the number of half-filled orbitals decrease, which also called as decrease in the melting point. This has a decrease, right? As I already discussed, yes, initially the number of unpaired electrons increases, but as you go from 3d5 or 4d5, pairing takes place. If pairing takes place, again what happens? If pairing takes place, again that will affect your melting point. But remember, there is still a rough trend in this. There is no true trend in this. Remember, that's what we discussed in the last slide. There is a rough trend, but okay, you can say that this is happening, right? So maybe some of the elements are following this logic. So now let's move to the trends in enthalpies, right? So this is the trend in the enthalpies. We can see this is atomic number versus delta H. So what is enthalpy? Enthalpy is nothing but enthalpy is the heat absorbed or released in a given process, right? So you can see here the trend in enthalpies is 3D less than 4D less than 5D. Why? As you go from 3D to 5D, the enthalpies are increasing. This is the reason. So greater the number of valence shell electrons, stronger is the interatomic attraction and stronger bonding between atoms, resulting in higher enthalpies of atomization. So here the enthalpies are the enthalpies of atomization. What is atomization? The ability for a given atom to form a bond with other atoms. This is called atomization. So greater the number of valence electrons you have, stronger is the interatomic attraction. So you have two atoms X and Y. So they have a greater attraction now. So once you have a greater attraction always, so you have the stronger bonding between the atoms, and what that results in? That results in higher enthalpies of atomization. So metals of second and third series have greater enthalpies of atomization than the corresponding elements of the first series. So you can see that the metals of second and third series have greater enthalpies. Why? Again, you know that in second and third series the number of shells is increasing. As the number of shells increasing, what happens is that the stronger interatomic attraction, the stronger is the interatomic attraction, and hence greater is the enthalpy of atomization. Now the new electron which enters the d orbital each time, the nuclear charge also increases by unity. But very important is this. Now shielding effect. You know that shielding effect is nothing but screening effect. So the penultimate shell electrons or the electrons present in the lower shells actually act as a screens for the electrons present in the valence shell. That is called the shielding effect or screening effect. But shielding effect of d electron is not that effective, hence the net electrostatic attraction is also affecting. So what is happening is that when the new electron enters in the d orbital, the nuclear charge increases, as I already told you, right? So as the atomic number increases, the nuclear charge increases, right? So the nuclear charge is actually related with effective nuclear charge by this concept. Effective nuclear charge is nothing but nuclear charge minus screening constant, which we generally discuss in the periodic properties concept. So nuclear charge is nothing but the atomic number. As the atomic number increases, nuclear charge increases. But what is effective nuclear charge? Effective nuclear charge is also depending on another factor, which is the screening constant. But what is happening to the screening constant or screening factor for the d electron? It is less. You can see that shielding effect of d electron is not that effective. It is not effective. So if it is not effective, the effective nuclear charge is increasing. So if the atomic or if the effective nuclear charge increases, it is nothing but the attractive forces by the nucleus on the electrons present in the outermost shell increases. So what happens? Because of that, the ionic radius decreases, since the increase in effective nuclear charge takes place. So this is a very important concept of atomic and ionic radii. So this is one of the reason why the atomic radii first decreases till the middle, becomes almost constant and increases towards the end of the period. So from trends in enthalpies we can understand how your D block elements, and I mean 3D series or 4D series, 5D series, why 5D series have higher trend in enthalpies. So even that concept of effective nuclear charge also gives an idea. Next important point related to this atomic and ionic radii. However, the increased nuclear charge is partially cancelled by the increasing screening effect of electrons in the d orbitals of the penultimate shell. So when the increased nuclear charge and increased screening effect balance each other, the atomic radii becomes almost constant. What happens is that we know that effective nuclear charge is Z minus screening constant. So obviously it says that as the nuclear charge increases, even screening effect obviously increases, right? So obviously this is increasing and this is increasing, but effective nuclear charge is almost same. So if effective nuclear charge is governing your atomic and ionic radii, so if the effective nuclear charge is almost same, so obviously your atomic radii or ionic radii, they also remain almost same. So when the increased nuclear charge increase screening effect balance each other, that means this increase and this increase are balanced each other because there is a minus sign. So if there is a minus sign, this almost remains same. So that's why your atomic radii becomes almost constant. So increase in atomic radii towards the end may be attributed to electron-electron repulsion. But if there is a case where your atomic radii towards the end increases, it's because the electron-electron repulsion. For example, you have an outer orbit and you have an electron in the penultimate shell. So this electron and this electron, if they repel, obviously the atomic radii sometimes increases. So in fact the pairing of electrons in the d orbitals occurs after d5 configuration. So we already know that pairing of electrons in d orbitals occurs after d5 configuration. So this is actually the graph of atomic and ionic radii. So you can see that the repulsive interaction between the paired electrons causes increase in atomic and ionic radii. So you can see that as I go from left to right of my d block elements or transition series, yes, it was following that logic that my radii should decrease because of increase in the effective nuclear charge. But if you are going to the higher atoms, you can see there is a slight increase. Why this slight increase is taking? This slight increase is taking because of electron repulsion. So yes, because of the increase in the effective nuclear charge, yes, your atomic radii or ionic radii is decreasing, but yes, your electron-electron repulsion for higher elements is causing the increase in atomic and ionic radii. So the repulsive interaction between the period electrons causes increase in atomic and ionic radii. So there is an increase from the first 3D to the second 4D series of the elements, yes, but the radii of the third or 5D series are virtually the same as 4D. This is due to intervention of the 4f orbitals, which must be filled before the 5D series of elements begin, right? So this is another reason for this statement, why the radii of the 5D series are virtually same as the 4D series. This is because now for 5D series, obviously you are, as I already told you in the introduction, you are having now 4f orbitals also. So these 4f orbitals should also be filled. So that's why they are intervening in between, and that's why the radii are almost same. So there is a steady decrease in the atomic radii from lanthanum due to poor shielding effect of inner core electrons, and there it is called a lanthanide contraction. So I will be discussing about this in detail in your concept of your F-block elements. Next, ionization enthalpies. So what is ionization enthalpy? Ionization enthalpy is the energy required to remove an electron from the outermost orbital in gaseous state, right? So now let's actually correlate the ionization enthalpy to your transition elements. One thing you know that ionization enthalpy is directly proportional to the effective nuclear charge. Ionization energy is inversely proportional to atomic radii. And another important thing is that ionization enthalpy is inversely proportional to screening effect. So due to increase in the nuclear charge, there is an increase in the ionization enthalpy along the series of the transition element. So yes, as the effective nuclear charge increases, ionization enthalpy increases. Next, ionization enthalpies give some guidance concerning the relative stability of the oxidation state. So ionization enthalpy, since you are removing electrons, so this removal of electrons is again connected to oxidation states. So that's why ionization enthalpies give some guidance concerning the relative stability of the oxidation states. Although the first ionization enthalpy in general increases, the magnitude of the increase in the second and third ionization enthalpies for the successive element is much higher. You always know that if you are removing electrons, and you always know that yes, the third ionization enthalpy is greater than, most of the cases, second ionization enthalpy greater than the first, because more and more the cations are formed, your effective nuclear charge increases or the radius decreases. That's why your ionization enthalpy increases. So we can see here from scandium to zinc, you know the configuration. This is the configuration. So if this is the configuration, you can see the ionization enthalpy values. So first ionization enthalpy, second ionization enthalpy, and third ionization enthalpy. This is the first, this is second, and this is the third. Right. So we can see that the third ionization enthalpy is greater than second, second is greater than 1. Why third is greater than second? Because of, for example, if there is a metal, it forms A plus, and then it forms A2 plus, and it forms A3 plus. A3 plus has less ionic radii or atomic radius than A, right? So if atomic radii decreases, you know one thing, that ionization increases, since I is inversely proportional to atomic radius. So the increase in is primarily due to increase in nuclear charge, which we know that. So as the transition elements involve the gradual filling of n-1 d orbitals, the effect of increasing partially cancelled by the increase in screening effect. So this is another concept, just like we have discussed for atomic radii, the same concept. Now screening effect also come to the picture. So the same concept, Z effective is Z minus sigma screening constant. So this is increasing, this is increasing. On the net, on the whole, the net is, this remains almost constant. So consequently, the increase in ionization energy along the period of d-block elements is very small. And this is the same thing, right? Enthalpy of atomization, 3d less than 4d less than 5d. So the same concept is used for ionization enthalpies. So what is the relationship between ionization enthalpy and stability? So with the help of ionization enthalpy, what we can predict is that, so you have two elements, the two elements are more stable thermodynamically. So when you have a metal, that metal is converted into M. What is M11? It is just M plus 1. So the energy required is I1 plus I2, obviously, right? So obviously, now if we are removing the electrons from a given element, obviously you have to provide certain energy, that is nothing but ionization enthalpy. So with the help of ionization enthalpy, yes, we can predict which of the two metals is in a given oxidation state is thermodynamically more stable. So when a metal M0 is converted into M plus 1, the energy required is I1 plus I2, or you can say that if it is plus 2 oxidation state. So you need I1 to convert into M plus 1, then I2 to convert into M plus 2. So if you want to have plus 4 oxidation state, that means you have to remove 2 electrons. The total energy is I1 plus I2 plus I3 plus I4. So you can see here, nickel I1 plus I2 is given, platinum's I1 plus I2 is given. So nickel's plus 4 oxidation state ionization enthalpy is given, platinum's is also given. So you can see that I1 plus I2 for nickel is less than I1 plus I2 for platinum. So what does that mean? It means that nickel 2 is more stable. So that's why you need less ionization enthalpy. Similarly, you can see here. So, to convert platinum to +4 oxidation state, this is the total ionization enthalpy. This is less than nickel. So, platinum 4 is more stable. So, what ionization enthalpy gives me idea is, it gives me the idea about the stability. So, lesser is the ionization enthalpy, more is the chance to form a given oxidation state. That is more stable. So students, in this part we got to know about the melting point and boiling point of the transition metals. We have seen the trends in the melting point and boiling point. We have discussed about the atomic radii, ionic radii, and we have also seen the trend. And last not the least, we have discussed about the ionization enthalpies and the stabilities accordingly. So in the next part, we will be discussing some more properties of transition elements. So till then, take care of yourself. Goodbye.